Quantitative Big Imaging, Lecture 10, Bimodal Experiments. So, until now we have been talking about mainly imaging with a single modality, and this lecture we are going to expand our views and look into combining modern imaging from more than one modality. Today's outline starts with some outline and scientific goals. Then I'm going to talk about image fusion and bivariate segmentation. This part will also continue with software engineering for repeatability and also adding the part that I didn't complete last week about visualization of the results. So until now we have been doing quite a lot. We are approaching the end of this class, and this actually second but last lecture. And we have been talking about image enhancement, how images are created. We also talked about some data sets and how you can use them for validating and testing your algorithms. And then we did some segmentation of different kinds and using the segmented objects to do shape analysis of different kinds. Going on with more advanced shape analysis, looking at distributions and thin structures. Then came the part with statistics, trying to make sense out of our data, because otherwise we only have a bunch of tables which don't make much sense. Last week I was talking about time series experiments and some ideas how to work with those. And that brings us to today's lecture, which is also a higher dimensional data set. And for that we need again some literature. So this is the recommended literature if you want to dig deeper. We have the general book, John Ross, Image Processing Handbook, which you have seen several times, but today we also add data fusion, image fusion of different authors. Also, again, we come to the image registration because that's also a central topic of the bimodal imaging, and yet another image fusion book. And until now we have, as I said, worked only with a single modality, so images from a single source, from a single type of radiation. And it's not always that it brings exactly what we need, or not the full story. And here are some examples from my work, looking at hydrology in soil and geology. Here the problem can be that the segmentation is not precise enough, maybe because of insufficient resolution or something. Also estimating the water content can be tricky, because you don't know if the water is really the origin of the change in the image. For cultural heritage, again, we have the segmentation accuracy. How well can you actually tell if that is a special kind of material in an object? And going on, again, more water. In this case, it's in building materials, where we again want to estimate the water content. And here the problem is that the objects often can change the shape or change structural changes, like cracks can be introduced due to the water coming in or going out. Then for material science, it can often be a problem with penetration power. So does the radiation you have chosen really penetrate the sample to a sufficient degree? And there can also be ambiguous readings, so the same contrast is shown for different things, and that can also be a problem that we want to address. So, how to select the modality? First, actually that's a general choice, and here we have some reasons to reject or select a certain imaging method. So on the good side, we choose one that has good transmission, so you really can penetrate with your radiation. You also should have good contrast, so you can see the difference between different features in the image. And with that also, ideally, materials can be identified or different structures can be well identified. To reject a method, we definitely look at low transmission, so it actually doesn't provide the information that we need purely in the sense of intensity. We may have low contrast, so it's very hard to distinguish if it's one material or the other. And with that, also not all feasible features may be visible. That could also be a resolution thing. And it could also be that the contrast between different features is too low and you cannot distinguish which material it actually is. And for now, we have only been working with single modalities, so we have to take like a all or nothing. So if you choose one, take the one that gives you the best. But what if we now would actually have the opportunity to add another modality which could fill in the gaps? And first we may look back to the concept of our experimental principle. So to begin with, we have our application, and with that we start asking, what do I want to see? How can I see it? And from that we go into the physics. First, on one side we have the physics of the material we want to investigate, but also the physics of the interaction between the chosen radiation and or a signal and the material. Acquisition is the part where we talk about the resolution you can achieve and also how fast you can acquire the images and with which signal to noise ratio. All those things go into the acquisition part. Next step is what actually this class mainly is about, is how to process the data in order to get the answers, to quantify the images, to get the answers for your application. So that closes the loop actually. So if we now would add a new modality, is to try to match the advantages of each method and kind of level out the disadvantages, and with that actually hopefully provide more information than if each modality was used alone. This could in principle in some cases extend the range of operation. It could extend the spatial or temporal coverage, so one modality may be faster but it doesn't have so high spatial resolution, or reversed. Could also help us to reduce the uncertainty. If we have in one modality, we may have good resolution, but we don't have the contrast sufficient to determine if this is one or the other item. And with that, we would also hopefully increase the reliability. And if we look at different modalities applied for material science, now I'm taking my main topic that I'm working with, so the neutrons versus the X-rays. And if you look at these periodic tables, you can see that both of them actually have very different contrast. So the gray level of each element corresponds to how large the attenuation coefficient is. And with that, you can see that there is quite a big difference between the two. And that can actually be used as a benefit if you combine the two. Otherwise, you have to select neutrons for one thing or X-rays for the other thing. And sometimes it's a tie, and then I would probably select the X-ray because that's easier to get access to. And another modality, or actually another method that gives more than a single image is the grating interferometry, where we on one side look at the traditional transmission, but you can also look at differential phase contrast or dark field imaging, and those all give different information, and that could of course also be combined into a final image. And that could be improve the physical interpretation and also give a motivation to fuse the information. And another way would be to work with spectroscopic imaging. So looking at not only a single wavelength, but also multiple wavelengths and combine the information into a single image. And that is often used for material analysis. And here you can see the Bragg spectrum from polycrystalline ion and single crystal spectrum from ion. And these two have very different profiles, and that can help us to determine what characteristics the ion has in the sample. For medical imaging, we can actually also in principle combine different modalities. We have MRI, we have CT, we have also PET and SPECT combining with MRI, and often one modality is able to capture sharp features with high resolution, while others may provide some functional information like blood flow and activity in the brain in this case. And that can also help then to identify different diseases in the patient. Looking at modalities in biology and microscopy. So here we have fluorescence microscopy, we have electron microscopy, and nanosims as spectroscopy, mass spectroscopy. And these examples also, as you can see, provide different information about the sample. Also at different scales. So if you look at the fluorescence microscopy, it's that little tiny thing, which you can see in the white box, and the red box correspond to nanosims. So here you also see the scale difference within the different modalities. And of course, you can also add further modalities and dimensions. In some cases, you only have a single point measurements or a scalar time series. Could also be that one modality provides only the surface information, and or you can compare single radiographs versus CT data, and that could in principle then, for example, provide temperatures or flow rates or pressure within the sample, combined with the image information that you have from one of the modalities. And the next part that we need, now we know that we want to combine different modalities, but what is the combining? What is actually the purpose of it? And here we come to the terms data and image fusion. And the definition is in principle that we have a theory with techniques and tools that are used to combine sensor data or also data derived from different sensors into a common format, that you have everything in one combination that brings the final answer. And in principle, the important thing is here that we want to improve the quality so that it would be better to interpret than it would be if each source was used individually. When it comes to fusion approaches, how you combine the data, then I would say there is no golden recipe. So the different fusion strategies we have is multivariate fusion, that all data are combined looking at in the same way. So you say you do filtering, you do the same kind of filtering on both. You would do segmentation maybe on both or combined or something like that. And every voxel corresponds to a voxel in the other image. Then we can talk about augmented fusion, that one modality is, say, contains the main information, but the second modality can help to identify the regions that we want to investigate. And with that, it would augment the output of the main modality. Fusion can also be used to reduce artifacts. So it could be that you can use the second modality to fill in the blanks or identify artifacts. So if one modality has a lot of outliers, we can certainly tell that with correct choices, can certainly tell that these are really outliers and not real information. And of course, as usually, combining everything is certainly also a way to go. So it may be that you do a little bit of the multivariate and add on with the augmented fusion. So the combination is certainly a good idea also to consider. And exactly how you choose the fusion strategy depends on, first, the experiment objectives, the sample composition, what can the sample actually deliver in the view of the different modalities. And availability of data can also be a criterion. What kind of data do you actually have available, or what method can you provide? And the condition of the data, it may be that the one modality is very blurry, while the other one has a very low signal to noise ratio. And with that, you also have to take care of them in a different way, and maybe that also affects your choice of strategy. Then there are different levels of fusion, that we have data to data, that would be actually comparing the images voxel-wise. But it could be that you also have data structures from one modality, and you want to have the output as features like segmented structures. Higher level, so this table goes down into more and more abstract information. So you could also do fusion between different features. So you have already produced features with the two modalities or the different modalities, each one, and then you combine it in the feature space. Going even higher, you can go into combining the features and bring out a decision. And finally, decision to decision fusion, that could be something you could actually compare it to maybe a random tree forest. And there you take the decisions from different methods and combine them into the final decision. Graphically, we can look at the image fusion workflow like this, that we have some images that we have acquired. They are in different modalities, different shapes, etc. Then we need to do some registration in order to bring the two images into the same frame so that we compare them. Then we have pixel fusion, where we first have to also do temporal alignment. So maybe there is a different acquisition rates and you have to match the two image sets to the same timestamps. The radiometric calibration, it could be that one modality has a different dynamic range than the other one, and here we talk about doing some kind of normalization. Could be just minus the average divided by the standard deviation. That would be a statistical normalization. You could do min-max normalization, but you can also do a normalization between the two. So you normalize it that this region has that kind of intensity and the same region in the other one, and you use that as a scaling factor. When you go to the feature fusion, Then you need to extract the features first. That's the first step. And that actually also requires that you already have done some kind of temporal alignment. Otherwise, it's very hard to compare the two. And within the features, you can also do some scaling, but that is maybe already done in a previous step. And then finally, you can also do decision labeling, and in the end, all gives some kind of fusion, and this fused data can be used for further statistics, modeling, etc. But it can also be used for presentation and display of the data. Of course, you can always do stupid things, so there is even a term called catastrophic fusion. And the definition of that is that combination perform worse than the individual modalities, so you're actually kind of destroying the data you have. So don't fuse because you have two modalities. Really be critical in what you do, and do the right thing from that. So the catastrophic fusion can be caused by selection of the wrong variables. So you're maybe actually looking at the wrong thing. There is no information to share between them. Could be also that you have too complex combination, that you try to bring in too much and it doesn't make sense. And then it could be that the sensor information cancel each other out. Maybe not so realistic, because every sensor gives some information at least. And if there is a linear relationship between the modalities, it means there is no meaning in doing the fusion at all. Then, important thing, I already mentioned it in the overview, is the registration. Is something that you need to do mostly before you do any fusion at all. And we already touched this subject last week when we looked at the time series, and it comes back again. And this time we are trying to do a registration between images with different information, different contrasts. And if you look at these two images, this is a neutron slice, tomography slice, and this is an X-ray slice of the same sample at the same position. And these we want to combine somehow, and the question is how. Looking at it, we can see easily that the sample container gives a bright contrast in the X-rays, while it's very low contrast for the neutron image. Then is the question how we can fix this. So the first part is finding the overlap of the cylinder is quite easy. I would say almost any registration tool would be able to find it. Next step is the rotation. And now comes the tricky part, because now we have strong features in different places of the image. In the end, it turns out that we need to first rotate the image to get it more or less in the right position. And finally, we also, you can see here that it's a completely different scale. We have almost 1300 pixels in each direction on this one, whereas we only have about 600. So there's a factor 2 in scaling between them. So after rotation, we also have to do the scaling so that we have actually the exact same scale, and also that the samples are oriented in the same way. You can, for example, see here is some kind of faint stone, and there is a gap in this one which has the same shape. So this, I would say, is the overlapping point. So when you do the registration, we already talked about it last week, and it's registration is an optimization problem, and the problem is that there are very many local minima, and it's very hard for the algorithms to really find it unless you give it a good start. So often we have to do some manual or guided registration to bring it more or less in the right region for doing the registration. Because if you are really way off, it's hard for the algorithms to find it. What you could do with a guided registration is you can identify landmarks or points, lines, planes or something that guides where to go. You could also provide a course pre-registration that you know that you need to rotate 50 degrees about to get to the right place. And after that, we can go on to the automatic registration, where we have the iterative process that we already looked at last week. The problem is that the multimodality has much less common landmarks, so that is something that the metrics must take care of. So last week we talked about the mean squared error, but that is often very misleading when you're talking about images from different modalities. So we need some kind of contrast intensity metrics. So one would be the mutual information, which is essentially the two bivariate version of the information theoretic entropy. Can also look at cross correlation of gradients and some kind of neighborhood descriptors, correlation ratio, and some kind of feature-based costs. So mostly a good start is to work with the mutual information and then go on to feature-based approaches if that is needed. So if the modalities are very different or if the data is very noisy. So what to do when we start doing the fusion? We can have, as we have said before, we have two tracks. One is the qualitative fusion, where we do the registration and co-visualization in order to see something in the images. And that is very often used, for example, in cultural heritage. You only have one sample and you want to show it, and you can spend quite a lot of time on doing nice renderings and artworks. And in this case, it was an interactive registration using VG Studio. And this sword was found on the Lake Zug. And it was in very good condition. So this is wood and there is amalgam. And, well, of course, there is steel. And the reason for using the two modalities is that this is a horrible combination for both modalities. And here we took actually really the best from each modality and could do a very nice reconstruction of the object. If you want to read more about this one, you can look at this paper. And I think there is even a YouTube movie where you can see how this one is rotating and separated in different components. And then we have different visualization methods. So let's start with some test data. This is a snail shell that we did with neutrons and X-rays, and here you can see a 3D rendering of it. And how we can combine this depends a little bit on what you want to see and at what stage you are in your analysis. One way, in particular, when you start doing the first steps, testing, evaluating, is to use a checkerboard visualization. And in principle, what you do is you alternate the tiles like this. This is modality A, B, and so on. And then you can see how well the two modalities match on each other. You can also see the contrast differences between them. This piece of code is essentially what is doing the mixing. Here I only used zeros and ones, that's where you see the checkerboard. But if you combine it into with two images, you can see the effect of the checkerboard visualization. And for example, here you can see how well, first of all, how well the registration worked. So it's actually a good fit. And you can see also what is the contrast in different regions of this. So the brighter background is with the neutrons and the darker are from the X-rays. Another way to visualize data is to use color channel mixing. And if you have 2 or 3 modalities, you can use the color channels of an RGB image. You could, for example, set that the red channel is set to the intensity variations of modality A. The green color is set to modality changes in B. And the last channel you can do as the average of the two, so it's more or less just an intensity scaling channel in this case. And often you want to normalize the intensity in the two, otherwise it can be that one is very dominant and that doesn't bring much. So here I try to do the channel mixing. There's a piece of code that is used for it. And here I even have this order. So 0 is red, green and blue. And if I permute them, then you get the different colors on the different channels. So here I set image A goes to red and image B goes to green. Looks a bit toxic. So yeah, it depends on your application if it makes sense to use this combination. Or you can take this one where A goes to B and to the blue and B goes to the green. Then you get more bluish color scale. Or you can say that image A goes to red and image B goes to blue. And this is actually a very nice combination if you want to visualize soil and water, because you have the brownish background and you have a lot of blue on the other modality. So it's up to what you want to show, but be aware that you have to be sure that you have a good normalization of the data. Actually, what I'm doing here is I'm doing a min-max normalization. Maybe you have to do some clipping in order to get it right. So now we only looked at the qualitative side, and we want to take the next step into segmentation. How can we use the two modalities to improve our segmentation? So if you look at the histogram of a single modality, with the low signal-to-noise ratio, it's hard to separate the two classes. You have a lot of misclassified pixels, but yeah, you have to do what you can with it if you only have this one. So if you look at the second modality, you are very unfortunate because it behaves more or less the same when it comes to the signal-to-noise ratio, but the difference is that now the responses for the two classes have actually flipped. So in this case, the orange one is the low contrast or the low gray level one, and here it's the high gray level one. And that gives us a little hint on what we could possibly do. So right now it's very hard to do a good threshold, but if we would combine them into a bivariate histogram, so that means every pixel in the 2D histogram is a combination, or count is a combination of what you have from modality A and from modality 2. And all of a sudden, this very hard to separate histogram has turned into something which is very clearly separable. So you can just easily put a threshold between these two peaks and everything is good. So this is the idea that we're going to use in the bivariate segmentation. So coming back to my favorite roots in soil, here we have a neutron slice where you can nicely see the roots in the soil. There is a bit roots over here too. You see the sample container. So this was probably some kind of plastic container. And in the X-ray slice, you only see voids where the root would be, and instead you see a stone. So it's very complementary in what you can see in these two. So if we look at the bivariate histogram of this one, you can see it's actually a logarithmic scale because the roots, they are very, very low count in comparison to the background. So this peak here would correspond to the background. And this is mainly the soil. I think that one was the container. And then we have the roots are in this part here. So it's a very low count for the roots because they are not very well represented. And now is the question how we can work with this, different segmentation methods. One would be to go into classical detection theory, where you do likelihood ratios between the images. And of course, it requires that you have well-registered images and also that the artifacts are corrected for. Otherwise, there will be certain misclassifications. So what you would have is the distribution of each of these different components in the image, and those you have to compare somehow. And until now we have looked into different segmentation methods when we have clusters of different kinds. So we looked at k-means, we looked at k-nearest neighbors, regression, neural networks, and those would probably all be relevant for this case. But let's look at something new. Here we have the Gaussian mixture model, which is a sum of Gaussian distributions in the image. And we have some amplitude, we have the position, and we have the spread. And for our test, we generate some data. And here we have some bivariate data. It looks like we have two chunks, two clusters. And we want to find them with the help of the Gaussian mixture model. For that, there are already tools in that we can use in scikit-learn, for example. And here we say we have a Gaussian mixture model, and we want to know a certain amount of classes. And then we say the random state, and we want to fit this data. And what I do here is I'm trying to fit 2 classes, 3 classes, 4 classes, and 5 classes. And with 2 classes, I think we have a pretty decent fit already. But let's look further on. The big on the top here is still the same, but the more elongated in this way is now split up in 2. And then when we do 4 classes, then the upper one is also split, and so on. So here you clearly have an over-segmentation, so many classes are not really plausible for this data. Now that we have, with the help of Gaussian mixture models, we get a model where we have a collection of Gaussians. But now we need to find out if a point in this fitted data is belonging to class A or class B. And the easiest way to do it is, in principle, a nearest neighborhood approach, where we have the distance between the points, and then we just compute Euclidean distance. And well, that works pretty fine, I would say. Well, there's always the ambiguity point, where if it belongs to this one or to that one, but that is the life of the whole thing. A different one is Mahalanobis distance, where you start bringing in more information about the statistical model. So here instead you have also the covariance matrix built into the metric. And then it's much easier to determine, okay, this one certainly belongs to this class here instead of that class, because now it's really clearly in the region of that one. One further is the Bhattacharya distance, which is again looking at the covariance matrix, but not only that, it's actually looking at the covariance matrix of the trained data and of the data of the measured point. So here it requires that you actually also measure covariance matrix for the measured point. So that requires more data before you can do a segmentation. data around the point. And here you can see when there is a good overlap between the point and its spread and the class that we have identified. As a summary, we can see the presentation of all three. So the Euclidean distance, just do a nearest neighbor. Mahalanobis looks at the shape of the distributions and see if there is a realistic overlap. So here you can really compute a likelihood. And finally, you go to Bhattacharya, which even includes the statistics of the measured point. Here I used the Euclidean distance, so the nearest neighbor, on the root data. And I got these classes that I identified. And that gives us a decision space looking like this. I even column mapped it so it corresponds to the different things in the image. So we have the blue one is the background, the brown one is the soil, gray is the container, and finally we also have the green for the roots. Now if you look at the segmentation, it doesn't really look that convincing. There are different reasons for this. One is the sharpness of the images, so they are quite unsharp, and that gives us this skin effect that I have shown before in multivariate segmentation. The other thing is that the roots at the container, they are marked up as the container, not as roots, whereas inside the roots we have container material. The reason for this is actually a combination of beam hardening and scattering, which gives a cupping effect in the images, which now brings us back to the point that you really need to have physically well-corrected images for this to make sense. So there is also another way we can work with the attenuation coefficient and working from the model of Beer-Lambert's law. This is a harder way because you can only have very few equations, and often it's not really easy to build up this equation system in a realistic way. The multimodal experiments, they are built up in different ways, but it can be that many multimodal experiments are done separately. So you do one scan at one scanner and the other scan at the other place. And that's because you have limited resources. You can't do it in one step. You can also maybe have the scanners in different places. It can be with different buildings, just different rooms, but you have to move the sample between the 2 points. Also, looking at the hospitals, you don't have an MRI in the same room as a CT scanner, so you have to move the patients between these rooms. Otherwise, you can also consider, if you do a very dedicated experiment, that you have dynamic experiments. Then you can go for the combined setups where you actually acquire the two data sets at the same time. And then here we have a setup that I'm using at the icon beamline, where we have the neutron beam that capture the neutron data, and at the same time we have the X-ray going across the beamline to do the X-ray tomography. And here you see clearly the need for doing the registration, because these two are about 90 degrees offset from each other to begin with. And the second is that the scale resolution is different for the two modalities. So we really need to have an intense registration task here. And this concludes the first part about the multimodal experiments. So the idea with doing experiments with more than one modality is we want to use the advantages of each to suppress the disadvantages of each. Of course, more data is produced, and well, that's something we have to handle. And The analysis must be adapted for each use case, but the important steps that we have is we have the registration as an initial step. We have the fusion, and finally also segmentation, and every step can take advantage of different modalities. And well, that's the end of this part, and let's go on with the visualization.